Good morning. I hope you're having a good day so far. We're going to take a look today, starting in on Chapter 7, about exponential models. And exponential, you can see, has something to do with an exponent. So we're going to take a look at what these graphs look like and then what their use is. It's actually pretty timely to be thinking about different types of models of data. There's all over the world, people are looking at models of data and trying to figure out what they're seeing and interpret it. So let's get you one step closer to being able to understand some of these things. Okay, so I have this exponential function, and just like we've done for most of the types of graphs, we're going to start by making an XY chart. And if we make an XY chart, I'm just choosing some X values to see what Y values we get as we go along and we begin to analyze this. So let's think this through for a minute. 4 to the negative first power. You should realize that that's 1 over 4. Okay, because that's what a negative exponent does. It may not show up good. Oh, here we go. 4 to the 0 power is 1, because anything to the 0 power is 1. 4 to the first power is 4. And 4 to the second power, 4 squared is 16. So what you do is you graph as many of these points as you actually can. So negative 1, 1/4 would be like here, 0, 1. Keep in mind there is a y-intercept, and that'll be important to us just slightly down the road here. 1, 4. And then you would draw in a nice curve to go with it. Okay. When we look at this curve, we notice that it's getting greater and greater and greater very, very quickly because of the exponent. We call this an exponential function, because the exponent means that at the ends it begins to get to be higher and higher and higher, or lower and lower and lower, until it is doing that very, very quickly because of the exponent. Now there's two possible things that can be happening. It can be either increasing very quickly, or it can be decreasing very quickly. We call it a growth if it's increasing very quickly, or a decay if it's decreasing very quickly. This one, because it's getting to be greater and greater and greater very quickly, this is a growth function. So when you are looking at these, I'm going to be focusing on some key points. I'm going to be focusing on your y-intercept, and I'm going to be focusing on whether it's a growth or decay, and then finding basically one other point just to give it kind of a structure to it, even though we're looking at a few points just here at the beginning, so you get the idea. Okay, let's take a look at another one. This one is 1/4 to the xth power. We're going to do some calculations, and then we're going to determine whether it's growth or decay. All right, so let's actually, what I'd like to do is I'd like to think about this in reverse order, because it's a little bit easier to think of 1/4 squared than it is 1/4 to the negative first. So let's think about that. 1/4 squared is 1/4 times 1/4, which is 1/16. 1/4 to the first power is a fourth, because anything to the first power is just itself. 1/4 to the 0 power is just 1, and that leaves us considering what happens when we take 1/4 to the negative first power. If you remember, with negative exponents, it ends up being the reciprocal. So the reciprocal of 1/4 is 4. So that value turns out to be 4. I have that written here a little bit nicer. And I did go ahead and graph it. You put the points that will fit on the graph right there so you can see what's happening to them. Okay, negative 1, 4, 0, 1, 1 to the 1/4, 2, 1/16. It's just getting closer and closer down to this x. Then we need to consider whether it's a growth function or a decay function. Growth means getting to be greater and greater and greater. Decay getting less and less and less. And what we see, this one from left to right is sliding down. So that would fall into the decay function category. When you see them in the graph, it's really pretty simple to determine growth or decay. And so let's just look at one more like that. Then we'll set up some rules and we'll figure out what we can use these things for in a more practical sense, because it's like, okay, great, I've got a growth function, I've got a decay function. What's that going to do for me in life? Okay, so here's another one. This one happens to have another piece to it. It's got this number out in front. It's only this 3 that's taken to the x power. The 2 is just another piece of the puzzle. So let's look at these various different calculations. When I bring this up, you're going to see the graph already made, but I want to go through the calculations for these and show them to you one at a time. Okay, so over here, if you focus on this rather than the graph for a second, when we plug in the -1 here, 3 to the negative first power is 1/3, so you're taking 2 times that, so you get 2/3. And when you look at the graphed point here, we have -1, 2/3. When I plug in a 0, 3 to the 0 power is 1. You don't multiply first, you go powers first. Remember way back when you did order of operations. So 2 times 1 gives you 2. 3 to the first power is 3. 2 times 3 is 6. And then we start going higher and higher and higher in value. 3 squared is 9. So we get 18. I didn't even graph 2 because that's way up here somewhere. But we have our graph going like this. You probably have already determined whether it's growth or decay. And it is growth because getting larger and larger and larger. And what we notice is this number makes those things happen even more abruptly, however not exponentially. Okay, so this number is more of a constant. This number is where our exponential growth is being determined from. But notice also that the y-intercept is different here. On the others, the y-intercept was 1 because anything to the 0 power is just 1. When you have a number out here, what it does is it changes the y-intercept. So let's analyze our basic exponential function here. As long as a doesn't equal 0, and for now we're going to also just say that as long as a is positive, okay? And as long as b is also positive, and we have an exponential function, we have some rules, some things that are going to happen. Okay, first of all, if we consider if this is greater than 1, then it's a growth function. Okay, if you remember from the examples that we just did, we had a fraction here one time, and that's when it became a decay function. So if it's a fraction or it's a decimal that's less than 1, it'll decay. But as long as it's greater than 1, it's going to be a growth function. Then you have this number that is not taken to the power. And if we have a number that is not just a hidden 1, then that's going to be where our y-intercept is. Okay, even if it is a hidden 1, this number right here tells us the y-intercept. So this number is important for telling us the y-intercept, and it will stretch it out a little bit if it's not, or it will scrunch it down a little bit. It'll make it a compression if it's smaller than 1. But this number being positive and being greater than 1 is growth, and less than 1 is decay. Now, there are some times when we always want it to be a growth, and sometimes when we'd hopefully like it to be a decay. on an exponential function. It depends on what that function is used for, but let's go through and just by the rules determine which ones of these are growth, which ones are decay, and where the y-intercept is. These are going to be your key things that you're looking for. Okay, so this 2 tells us something. This 2 tells us the y-intercept. This number is going to tell us whether it's a growth or decay because these are all exponentials. So this number greater than 1 means that it's a growth function, and the 2 tells us that the y-intercept is 2, so crossing the y-axis at 2. 1/5. Hopefully you're just figuring these out ahead of time. Less than 1 means it's a decay function, and there's no number here, which means there's a hidden 1, so our y-intercept is 1. This one, greater than 1, makes it a growth function. This being a 4 means that's the y-intercept, so the y-intercept is 4. This one, even with the decimals, whether it's decimals or fractions, this number is smaller than 1, which makes it decay, and the y-intercept is 0.5. So just giving you a general idea of what's happening with these functions. Okay, if you have something in finance, you're going to want it to be a growth, and if you have something in like where you're trying to control disease, you want it to be a decay as far as less and less and less cases on something like that if you have an exponential model happening. Okay, so once again, here are those, but over here we're going to take a look at what the graph is. What I want you to do when I see a graph, okay, now this will be a little bit more difficult as far as when we come to testing, because I am going to have to see your graphs, so there'll be a little bit of emailing and special instructions for that. But what I will look for is I'm going to look for definitely the y-intercept. So your first job on all of these is going to be to just graph the y-intercept. And we know the y-intercept is easy to find. It's just this number right here. So this one, your first point to graph would be a 2. This one, the first point to graph would be a 1. This one, your first point to graph would be a 4. And then this one, our first point would be a half. We already determined whether it's going to be growth or decay. So what you need to do is you need to find one other point that's graphable in order to make this work. So for example, on this one, your one other point that's graphable, well, x to the first power, that's great. That's going to give you a 10. That's way up here. That's a little harder to find. But if you have x to the negative first power, that will give you 1/5 here. And 2 times 1/5 is 2/5, and that'll give you a point right down here. That's enough for you to figure out what's happening. It's not going to go down past the x-axis at all. So your graph will look like this, and that's going to be what I'll consider to be good enough. Now you kind of have in your mind that this next value is a 10, so you know it's going to be heading up this way. It never technically goes completely vertical, but it gets very, very close to vertical when you've got this exponential growth idea happening. So you're making sure that you graph 2 points and then putting in your curve showing the exponential growth on that. This one we know is going to be decay. So we can think about the points. We know the y-intercept is 1. We've already graphed that. Okay. You can then say, okay, well at 1, I know my value is going to be 1/5. And you're already expecting it to decay, so that actually makes sense to you. You've got your 1 graphed already. You're going to graph your 1/5 point, and I'll expect to see something that looks like this. Over here, you've already graphed your 4. If we put in a 1, you're going to have 8. That's okay. You could graph the 8 if you wanted to, but if you put in a -1, this becomes a half. 4 times a half is 2. So there's that one. Like I say, the 1/8, That's all right, but you're going to have to bring it down to decay. So it's kind of better to check out the -1 on that. So, because that's going to bring you down closer to this x-axis, which is where we're heading in the first place. And these numbers exponentially grow so fast, it's sometimes very difficult to find where the next point is in the positive direction. So that negative exponent is going to be your friend in these for the growth functions. In the decay functions, you're probably going to want to look at the next positive number. So we know that this already has a y-intercept of 1/2 from here. And then you plug in a 1 here, and that'll give you 0.2. And you can graph that, and you have your pretty good little sketch just to get you going, to have something to show me as far as what your graph would look like, and then the analysis could happen. Now, what's this used for? What this is used for is for functions that will show an exponential growth. Like, for example, if you have money in a bank account and you have an interest rate, and you leave that money alone, it's going to grow, and it's going to grow, and it's going to grow through different time periods. Okay, some are growing incrementally. So in other words, the interest is put in like maybe once a year. And if that interest is put in once a year, you would use a function like this. It's a growth model. Or if you're losing money, then it's a decay model. Okay, and it is exponential based on the interest rate. So we're going to take a look at that. It's also used for models. Sometimes biologists will use it if you have something where you've got an exponential growth happening in a petri dish, where you've got some kind of a cell and it's dividing in 2 and dividing in 2 and dividing in 2, so you have twice as many cells and twice as many cells. That's another example of something happening that's using a model such as this, but we need to take a look at what all of these variables and things represent. Okay, so this lowercase a here is the initial amount of whatever it is that you're starting your growth or decay model with. So it can be the amount of money that you're investing, or it can be the original amount of bacteria that are in that petri dish that you're studying about, or a starting population of a certain endangered species, and you're hoping that you have an exponential growth of their population as you're putting them into their habitat and expecting the amount to grow. But the starting amount goes right here. This is our rate of growth. Okay, this amount would have had to have been calculated somewhere. If you have a bank, there is a growth rate or an interest rate that they give you. It needs to be put in here as a decimal. If you're a scientist, you might be able to calculate the rate of growth if you determine that you've got an exponential model happening, and then you can figure out what to expect in future times. Or if you find that there's an exponential rate of decay, then you can figure that all out also. When you're doing other types of things, you're looking hopefully for a rate of decay, so that if the function is exponential, you want certain things to be going down, 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 instead of up, 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 up. Okay, and then the t is the number of time periods. Okay, so if you have a growth rate per year, then t has to be in years. If you have a growth rate per week, then t has to be in weeks. Not every function is exponential. We know that some come out to be linear, some come out to be quadratic. Remember, we did regression equations. Those were for the other types of growth, but this is a different type of model right here. And then this is our total amount that you get after that amount of time periods. Okay, this is a very, very important formula for many different types of analysis. Okay. All right, so let's take a look at an example. All right, you invested $1,000 in a savings account 6 years ago. And sometimes we do that. We say, okay, this money I can do without, but I've got a long-term goal. Maybe you want to purchase a car or something like that, and you put the money in, you're saying, I'm not going to touch that. Or for you, you might say, well, I know I need to pay for college, so maybe several years ago somebody put money into an account for you, or you put money into an account yourself for something like that, or you're going to save up for a house, so you put that money in and it's untouchable and you've managed to lock in a certain interest rate. Okay? Now, we will later on talk about what happens if you have something where the compounding is continuous rather than in time increments, and we'll be analyzing which is better. But for right now, we have this formula where the interest plops in once a year, and then that amount gets used for calculating the next year's interest, and so on and so forth. So we're going to use our formula. We want to know how much you have at the end. The starting amount is $1,000. Our growth rate is 5%. So as a decimal, that's 0.05. Don't forget, when you have a percent to a decimal, move your decimal place too. And 6 years, because annual means once a year, 5% every year. And so there's your exponent. So what you're going to do is you're going to add those two numbers, and then you can do the calculation. This is where that caret key is going to come into play in your calculator. Or if you needed to, you could multiply 1.05 times 1.05 times 1.05. Not nearly as efficient as putting it in like this. I have 1,000 times 1.05 to the 6th power. Now this calculator will do order of operations, so it will take exponents first and then multiplication, so you're safe with that. I did put up on there, there is Texas Instruments themselves is offering a virtual download for during this. If you follow through and click, I put a link on the bottom of your page, not for this one, but for the 84 plus. So that's kind of cool. So you can go through and follow the prompts on that. I put the link down, so that might be helpful to you for your PC if this one doesn't work anymore. And this one doesn't work on a lot of computers anymore. And Wabadimoo only works on your Androids. So iPhone users, we've got to find something else. Okay, so here's our number. Now we're talking about money here, so you need to round to the pennies place. 1,340, you would round to here. This 5 bumps it up, so $1,340.10 would be the amount that you would have now after that 6 years. So that's pretty nice because the growth was exponential. Way better than if you just took 5% of the 1,000 every year, because each year it's growing based on the previous year. So that's pretty good. So you've got that $340 extra that you wouldn't have had if you didn't just leave that $1,000 alone. Now, this 1.05 is an important number. This number is what we'll call the growth factor. Okay, so our growth factor is what happens when you take your interest rate or your rate of growth or decay and you put it with this one. Now, the two examples that I have today are showing a growth, okay, but you can sometimes have a decay. There can be sometimes something that is eating away at the money that you have. We hope that you don't get into that situation, but that sometimes happens. So people use that as also as a thing that can happen. Or you can be looking in biology for something that you want to have a decay rate because you want a certain thing, a certain virus or something else to be going down, 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 down instead of up, 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 up. So we have those things. So sometimes a decay rate would be good. So a decay rate would be a negative number here. And so if you had a negative number, this growth factor would be less than 1. So sometimes a growth factor, like in finance, is good, but sometimes when you're fighting a disease, a growth factor of less than 1 would be better. Okay, so we've got an investment of $500, a 5-year investment, the account paying 2.3% interest. And so once again, we plug in these numbers. 500, 1 plus 0.023, you bump the decimal point over 2. Fifth power, because it happens over a period of 5 years. And then you can use your calculator. 500 times 1.023 to the 5th power. Okay, we got to round to the pennies place, and yes, that is important. 560.21. So $560.21. And you got the extra $60 for leaving the money alone if it's compounded annually. All right, so sometimes things are compounded annually, sometimes compounded continuously, but this formula works for annual compounding. And so it is a growth factor of 1.023 because this is the number that you use for that. All right, that's it for today, and I wish you God's blessing. Have a great day.